Graphical analysis. It is time to summarize what we have learned about graphing in this unit and learn one more cool idea. The slope of a position-time graph gives us velocity, and the slope of a velocity-time graph gives us acceleration. If an object is moving at a constant velocity, it will have three graphs that could look something like this. So if this is the position graph, the slope of this line is 3, which means the velocity of the object is 3, and it's constant, which is why it's a horizontal line. The slope of a horizontal line is 0, which is why we get 0 as our acceleration graph. If an object is moving with a constant acceleration, it will have three graphs that could look something like this. So remember, constantly accelerating, you get that parabolic shape. You get a parabola. If you take the slope of the tangent line at various points, you will get the values of velocity. See, at this point, at the origin, position of 0, the tangent line is a horizontal line. The slope, therefore, is 0 at that point. But if you go over here, you get a slope, let's say, of 2. And so you'll get a value of 2. Up here, you might get a value of this, the slope of this tangent line might be 4, which means you'll get a value of velocity of 4. This is how you end up with a line at an angle for your velocity time, right? Because your velocity is increasing with time. The slope of this line is 2. That is your acceleration. If you have a position versus time graph, just take the slope of the graph at multiple points and plot those values to get the velocity graph. Do the same thing to the velocity versus time graph to get the acceleration graph. So from position to velocity, you take the slope. From velocity to acceleration, you take the slope. But can we get information about position and velocity if we're given an acceleration graph? Yes. If you calculate the area from underneath an acceleration graph, you get the object's change in velocity. If you calculate the area underneath the velocity graph, you get the object's change in position. Let's examine how this works. Let's first look at an example with 0 acceleration. The area under the curve, which really means the area between the graph and the x-axis, is 0. Therefore, the object had 0 change in velocity. Since acceleration is, by definition, change in velocity over time, if the object moves with a constant velocity, the acceleration is 0. In this example, the acceleration is at a constant value of 2 meters per second squared. The area underneath the curve from 0 to 2 seconds is 4. The area of a rectangle is height times width. In this case, height is acceleration, and width is time. Acceleration multiplied by time gives us our change in velocity. Here's the first kinematics equation. Subtract v naught to the other side. V minus v naught by definition is delta v, change in velocity, equals acceleration times time. That is the area of this rectangle. 2 times 2 gives us 4. That is the change in velocity. It is important to note that we can only calculate the change in velocity through this method. We cannot know the exact values of v and v naught. Both of these graphs show us a change of velocity of 4 meters per second. In fact, there is no way to know v naught and therefore the y-intercept. So either one of these graphs could be the velocity graph for the acceleration graph on the previous slide. If we have a velocity versus time graph, the area underneath the curve gives us the change in position. This graph shows an object moving with a constant velocity of 3 meters per second. The area under the curve from 0 to 1 second is 3. Therefore, this object has moved 3 meters during that 1 second. Remember, delta x change in position equals vt. This is the second kinematics equation without acceleration. Vt, well, that's velocity, the height of that rectangle, times time, the width of that rectangle. Therefore, that is the area underneath the curve, 3 meters. The same strategy works when the velocity is not constant. The area underneath this curve from 0 to 2 seconds is 4. You just have to calculate the area of a triangle. Therefore, the object's change in position is 4 meters. Once again, we can't know the y-intercept here. We don't know the exact values of x and x naught. Either one of these graphs, or an infinite amount of other graphs, could be the matching graph for this velocity time graph. When we say under the curve, what we really mean is the area between the graph and the x-axis. If a graph goes below the x-axis, see how this is 0 here? Then we're actually going to be calculating the area above the graph. So here is a velocity versus time graph. From 0 to 4 seconds, the change in position is 0. Displacement is 0. By the way, this graph might be an object that has been thrown straight upwards. It slows down, comes to rest, and then speeds up back towards where it started. By the end, it ends up exactly where it started, so its displacement is 0. When you're calculating the area above the x-axis will be positive, area below it is negative. That's why they add up to 0. However, if you're trying to find the distance traveled, that is different than displacement. Distance traveled is always positive, as indicated by a car's odometer. The odometer is going to measure how far your car has gone. It doesn't care what direction you went in. So while this object's displacement is 0, its traveled distance was 4. So you're just going to treat this as a positive number instead of a negative number. Add them together and you get 4.